Okay, guys, I want to go over some of the semester exam review with you since I will not be in class with you when you guys take your actual semester exams. I'm going to give you some key hints and some tricks and kind of go over some of the styles of questions that you're going to see on the test. And then go over also what I'm going to give you that you can utilize on the test. So station number 2 is the conservation of mass. So when we talk about the conservation of mass, it just means that whatever mass we start with is the same mass that we have to end up with. So for the first question, it says, what will be the mass on the scale on the right? So if we start off with 300.23 grams, we have to end up with 300.23 grams, okay? Law of conservation of mass says whatever you start with whatever mass you start with is the same amount of mass that you end up with, regardless of the experiment that's going. Okay. This one here, there's again that same idea. So whatever mass we start off with on one side has to equal whatever the mass is after the chemical reaction. That's what that arrow means. We'll talk a little bit more about that in one of our next couple of units. So the easiest way to do this, and I know in first period when we were starting to go over it yesterday, kind of made it a little bit more difficult than I needed to, but if you look here, you can add up the two masses here, you get 256. You know, that mass has to equal this one. So 152, you can subtract it, and then you get the amount of zinc, so 104 grams. Okay. The law of conservation of mass states the starting mass is equal to the ending mass. There is a lot more scientific, technical way that that's stated, but that's the idea. Whatever you start with mass-wise is what you're going to end up with mass-wise in an experiment. Okay, then it talked about heat transfer. So the key in there is heat always travels from hot to cold. Okay, this one here asks you to draw a diagram of that and show the flow of heat energy with an arrow. So it's always going to travel from hot to cold. Okay, so that's what I did with this particular one here. Drew an arrow from the warmer section to the cooler. What term that you may see on the test is what we refer to as thermal equilibrium. Heat, the same. So as that energy is transferring from the hotter to the colder one, it does become a point to where these two are going to be closer to the exact temperature. So in the particular question on your test, it's going to talk about it cooling. So remember, if it's getting cooling, and this the left side is transferring heat. The thermal equilibrium for this one obviously would be 50, where they were both equal to 50 degrees Celsius. Okay, so thermal equilibrium just means heat. Thermal is referring to heat. Equilibrium, equal, so the same. Okay, nomenclature. So there are going to be, I think there is one question on the test about nomenclature. So one of the things to remember is that when we talk about ionic compounds, this is your metals and your nonmetals on the periodic table. So I did have a couple of you ask me, well, how do I know? And I know that I have taken your journals. So what I'm doing is I'm providing you with a periodic table. You can clearly see that it is colored on there, so it's referring to where your metals and your nonmetals are, okay? So your metals are going to fall on pretty much the left side of the periodic table. We have what we call the staircase. That's here. You can kind of see it in that blue color. And everything to the right of that staircase is going to be considered your nonmetals. So when we look at nomenclature and the rules for nomenclature, and we're looking at the metals and the nonmetals, what it comes down to with that one is making sure that they have balanced charges. So if you remember when we talked about this before, that metals were more likely to give up an electron in order to form a particular compound. Okay, so the group number is going to determine how many electrons that a particular element is going to want to give up. Okay, so what do I mean by that? So what we're looking at here, okay, is that typically in this first column here are elements that are there, with an exception of hydrogen. Hydrogen is over here with these metals. Excuse me. So these metals here are going to give up an electron in order to combine with a nonmetal. Okay, so depending on how many that we have in each of those particular areas is going to determine how many of each of those atoms you would, the element you would need in order to create a proper chemical compound, and then also too that goes back to the naming. So if you look here, this first column is a +1. Okay. Second column +2. Third column +3. That means that they're willing to give them up. So they're turning positive. Remember, if the more electrons that an element loses, the more positive that it's going to become, because it has more protons than electrons. Okay. And that's in a neutral. For the fourth column here, they will either give up electrons or take in electrons. That's what the negative refers to. Okay. And then nitrogen. So now we're getting into our nonmetals that are going to want to take those particular electrons in. Okay. So positive. So our metals are going to give them up to the nonmetals. Why is that important when it comes to naming? Well, when it comes to naming, what you will typically see, depending on what the elements are, you may see where we have two elements. So let's say we have element A and element B. When we write their chemical formula, okay, you may see where we have those subscripts. This is just telling us how many atoms of A are present in the compound. This is going to become important too when we talk about molar mass here in just a second. Okay, so what are the rules? So basically, the metal will keep its element name. Okay, and the nonmetal will have the ending changed. Okay, and I'll show you what I mean by that. So, it typically ends in ICE. With our covalent compounds, these are going to be 2 or more, there can be more, nonmetals. Okay? And when we deal with the cases of covalent bonding, if you have 2 or more of the element or atoms, okay, or even in cases where we have 1 atom, and I'm going to put in here second element and explain what I mean by that here in just a second. But again, let's say we go back to these 2 elements here. Once we see that there's more than 1 atom, or even if there's 1 atom, when we do the naming piece, we have to use the prefixes. So if you remember, we would have mono, 1, di, 2, tri, 3, and so on. Okay, so if we were to write out, and I'm going to show you examples here in just a second of what this looks like. If these were 2 nonmetals, this one would be di, whatever element this is, and this one here for B, that second element, would be mono. Right? You will not see mono on a first element. So let's say if we have a compound, let me do CO2. Okay, so if I were to write this out, it's carbon. We don't have to account for that one there, and then dioxide. Okay, that would be the proper naming. So when it comes to the nomenclature on the test, there is one, and the answer is in here. So the easiest way, and my biggest suggestion to you guys when it comes to this, is look at the chemical formula. So we have NaBr. Okay, take your formula chart. I'm going to find Na. So I have sodium. If it's asking me to match the name or to find the name in a multiple choice, I know sodium is here, so I just have to find where sodium is at, okay? You can kind of look at that first element, even if you don't remember the naming rules, and determine which ones match with which, okay? So Li is lithium. So there's Li right here, lithium. I only have one lithium, so lithium sulfide. So again, this is where your metals and nonmetals. So if you notice here, even though we have a 2, we don't have to use those prefixes. It's only going to be if we have 2 nonmetals. We have Ca and B. So Ca, if I look at my periodic table, is calcium. Okay. So then I look over here, which one has calcium? So we've got calcium bromide. Okay. Then we have nitrogen and oxygen. Okay. So N. Now, if I notice here, those are my 2 nonmetals. So if you look here, nitrogen and oxygen are together. They're to the right, so that tells you that they're the nonmetals. So because they're nonmetals, we're going to have to account for, do they have more than one atom? They do. So this one would actually be di, so 2 nitrogen. Even if you don't remember the naming rules, if you look here on the side, there's only one of them that have nitrogen in there. So even if you can identify the elements, if it's asking you to determine what the chemical formula is or what the name is, just look at the element and then find the one that's the closest to it with matching on the test. So we've got carbon and oxygen here. So again, 2 nonmetals. I didn't look those up on the periodic table because hopefully by now you can look at C and O and know that's carbon and oxygen. So if I look over here, I've got carbon tetrachloride and carbon and then monoxide. So I know that this is oxygen, so I know that has to be part of it. So, and if you look here, we don't do mono for the first one when we talk about covalent bonding, which is what this one is here, or covalent naming, excuse me. But we do have to account for it in the second element, so monooxide. So mono means one. Okay. We have aluminum here, Al. We've looked at that one several times. So aluminum oxide. Okay. Carbon. There's the C again. This one right here, just so you guys know, if it's an L. If you see a C with what looks like the straight line after it, that's the L. And you can also tell because of the 4 afterwards. I know a couple of you guys struggled with that one. So this one, though, is carbon. So I'm going to look over off to the side, and I see carbon up here. Okay, so carbon tetrachloride. And then my last one, sulfur and oxygen. There's only one that's left, so I can match that one there. I will tell you the answer to, or the question for your semester exam is one of these 2 here. It is going to ask you to name. And again, one of the things that we did do with the semester exam is we did do everything as a multiple choice. So again, look at that first element or look at whatever elements that they give you. Find the letter. Okay. And even if you're not sure completely with the naming process, you can do a process of elimination. We're not into the gotcha piece. Okay. What are the trends on the periodic table? So I gave you guys this periodic table trends. I'm going to give you another one as well to help you with the test. But these are all the trends that we have. So we have electron affinity, atomic radius, electronegativity, ionization, metallic characteristics, non-metallic characters. And you'll see that for each of the different trends, you'll have what direction that they're flowing going in the columns, which you remember are the families, and which ones and what direction that they're going to be increasing in the rows. So whatever direction that arrow is pointing to is going to show where it's increasing. So for instance, atomic radius increases as we move down the columns, and then as we go from the right to the left. The question that, sorry, didn't get all the way, that you're going to be asked is either going to be about ionization or electronegativity. You will have this chart here. So what you're going to have to do is you're going to have to look at your trends. So let's say it's ionization. I know that as I move from the left to the right, ionization is going to increase. And as I move up, or from the bottom up, ionization increases. So you're going to have to do some comparison on the periodic table itself in order to determine what particular elements. They give you a list in the question, which ones are involved. So that's kind of covers the trends that are on there. Okay. This one says arrange the elements Ca, Mg, Be, Ba, and Sr in order of increasing ionization energy. So you're going to have to look to see where they're at on the periodic table. So I have Ca over here. Okay. And I have Mg. Okay. So there, it looks like a lot of them Be, Be, Ba, and Sr. Okay, so basically it's this one right here, this second column, and it's wanting us to rank in an order. So if I look at my trends, which again, you're going to have this, it tells me that my ionization is going to increase as I move up. Okay, from the bottom up. So if it wants me to rank these in order of increasing ionization, my very first one is going to be whoever's closer down here to the bottom. Okay, because remember, as we move up the periodic table, our ionization increases. So if I look, Ba is actually the first one, the smallest one here. And then Sr, so the next one above it, because we're basically using these elements here in this particular one. So Ba, Sr, then after Sr is calcium, so Ca. And then above calcium is magnesium, Mg. And then your last one is beryllium, B. Okay. So again, you're going to have your trends table. So you just have to pay attention to the direction of the trends. And typically in this case, we usually ask, we're going to ask about elements, I believe, in the same column. So remember, from the bottom up is going to show you the increase in ionization and ionization energy for those elements. Okay. Lewis dot, there are going to be Lewis dot ones. So I gave you both carbon dioxide and water. So when we draw a Lewis dot structure, we have to pay attention to the amount of electrons that each of these elements can give up. Okay. So when we look at carbon dioxide, and one of these two is going to be the test question. Okay. Carbon is in the fourth group here, and then oxygen is over here in group 16. If you look here, in order to write this out, and when we have to pay attention to it, is that these numbers are also here, if you remember, represent the valence electrons, which is what a Lewis dot structure represents. It's the number of valence electrons to show the bonds between elements that create a compound. So in this case here, carbon is going to be willing to give up or take in up to 4 electrons. Oxygen is, a single oxygen is going to give up 2 or take in 2. Excuse me. So that's why there's the negative there. So if you look here, carbon dioxide. So if I were to write this out, carbon, and then the di here, remember we talked about the naming, the prefix is telling us there's 2 oxygen. So that's why when you look here, carbon dioxide. So what is this going to look like for a Lewis dot structure? Okay. So C is going to be in the middle of this one. Okay. And then we have 2 oxygen. Okay. So we're going to put the oxygen on either side. So what this tells us here is that it says that carbon is going to be sharing its electrons with the oxygen. And then oxygen's here. Okay. There's going to be 2 of those there. And so we have to account for their bonds. Okay. So paying attention to where they're actually at with the groups. So oxygen, I told you guys, was in group 16, and then carbon is in group 14. So one of the things, and it wasn't the negative ones necessarily that are representing the valence electrons, it's the groups. Okay. So the group that they happen to be in. So over here, for instance, we have 18, 17, 16, oxygen 16. So there's 6 valence electrons. Nitrogen is 15, 14, 13, and then 1 and 2. Okay. So carbon has 4 electrons. So we've got, and this one here and then oxygen has 6. So we're going to do the oxygen one first. So if you remember when we write the electron configuration, we're going to put dots around it to represent each of the electrons. Now, for carbon and oxygen, it's a little bit different. They actually form what we call a double bond, which means that typically when we write a Lewis dot structure, we're going to write the electrons, the valence electrons, all the way around that particular element. So, for instance, oxygen would have necessarily, if we just wrote it, would have 1 on either side. But because there's a double bond created between them, we're not going to put any dots here. So when we ask you to find the Lewis dot structure, you're going to look for one where you're not going to see those dots over here on the right-hand side, okay? Carbon has 4, and again, like I said, with this one here, it's a little bit different. They actually double bond, so rather than put them all the way around carbon, so normally if we were drawing a Lewis dot structure, for instance, for carbon, it may look something like this to tell us that it wants to pair. But for carbon dioxide, it creates that bond, and that was in some of the activities that you guys did as well, okay? So if we're looking for what a Lewis dot structure for carbon dioxide looks like, it's going to have C in the middle and then the double bonds. Okay. For water, water is H2O. Okay. So when we draw out that particular Lewis dot structure, we have oxygen, okay, and then we have 2 hydrogen. Okay, you'll typically see that it's a bent shape. We're going to talk more about shaping later on in other units, but again, oxygen is going to have 6 valence electrons. Hydrogen is in that first column, so it only has 1 electron. Okay, so when we draw up the kind of their Lewis structures, and then for oxygen, they're going to have to bond together. So when you see water, you'll have oxygen appear first, okay? And then you'll have hydrogen, which is giving up 1 each. So this is the shape there. One of these 2 is your answer today, okay? So make sure, or when you take your semester exam, because I know some of you are watching this the day of your semester exam, and then some of you will be watching it the day before. But one of these 2 is going to be the answer for your semester exam. Okay. So there's a little bit about periodic tables. The next one is looking at the emission spectrum. So on mine, I know it's in color. On yours, it will be black and white. I had a couple students ask me, well, how can I tell if it's in black and white? You're looking at the band. So basically, when we look at different elements, they emit different light frequencies. And so that gives them their unique characteristics. So if I look at this one here, this unknown, I just need to compare with another element here, a known element that has similar structures. So I have this one here. We've got beryllium, but it doesn't really follow beryllium. So I'm going to keep going. This one is a little bit, manganese is a little bit off from it. But as I move down, you can see where strontium pretty much matches up with it. So let me look at the next one. So there's 3 there in the unknown. There's 3 in strontium. And then as you move further down, you can see that those actually line up. So it says, what element is the unknown based on the picture above? Okay. And then what does the electron emission spectrum tell us about an element? It's basically just letting us know what kind of electrons are present, how active they are, because remember, as the electrons move around, we saw that with that flame test, they emit different colors of light. That's basically what they're made of, what makes up that particular element. So you will have one of these on the test where they're just given the picture and you just have to find which one matches it. Okay. Electron configuration. So Again, I gave you a while back when we did this, a periodic table that looks like this. I am giving you this for the test as well. So electron configuration is just basically a different way to kind of roadmap where an element is on the periodic table. So for instance, if it's asking you what the electron configuration is for boron, we've got boron over here. Okay. So as we look at our electron configuration, we're moving across. Okay. So each of these represents one spot. So the way that this would start would be 1s2 because it's the section for the helium, or excuse me, hydrogen, and then helium. Then we go to the next one. So now we have 2s, and then each box is going to be apart. So then we would have 2s2. And then we have boron, which is right here. So then we would have 2p1. And this is just basically the electron configuration is kind of like the address for the element. It's another way to identify where it's at. So this is what it would look like for boron. Okay. For calcium, or excuse me, for carbon, carbon is the next one over. So it's kind of following that same pattern. They're going to start off the same because they're having to follow the same pathway. But because calcium is 1 over, and we're now in the P1, it would be 2P2. Okay. And then the last one, the other example I gave you is beryllium. So we're going across here. Okay. Sorry. So we've got 1s2. So our s orbitals can hold up to 2 atoms. And then you'll notice here that then we go into the second row. So 2s, and then the beryllium is right here. So we're going to stop at this one. So then it would be 2s2. Okay. One of these, again, is your answer for the question on your semester exam. But again, you'll have this to where you can follow. So again, each of these represents a spot in the orbitals. Okay. So S's can hold 2. So up to 2. P's can hold 1, 2, 3, 4, 5, 6. Okay. So if you notice those boxes, each of those boxes represents a spot for that orbital. D's, okay, so we go into, depending on where the elements are down here, you'll notice that we go from 3p and then 3d. These are those transition metals that follow a little bit different pattern. But D can actually hold up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so D can hold up to 10. Okay, but again, one of these here is your answer. So just follow along, find out where it is, match your periodic tables, find where that element is, and then once you get into that region, you just have to count how many boxes over it is, and that becomes your superscript to identify how many atoms are in that particular, or excuse me, how many electrons are in that particular orbit. Okay, so again, one of those is your answer for today on your semester exam. Okay, so we have those. So then when we're looking at, you will have one of these as well. It's going to ask you for the valence electrons here. So these are the outermost shell. Okay. So how many does atom X have? There's in the outermost shell, atom X has 1, atom Y has 1, 2, 3, 4, 5, 6, 7. Okay. Which group would X and Y be in based on their valence electrons? So if you remember here, I just told you guys that the group numbers, okay, so this would be group 1, group 2, 13, 14, 15, 16. The group numbers, whatever that ending number is, if it's a double digit one, is going to tell you how many valence electrons. So if atom X has 1 valence electron, it's going to be somewhere in this first column. If Y has 7, it's going to be somewhere in 17. Okay, so the groups will match the valence electrons. So group 1 for X, and group 17 for Y, based on their valence electron. Okay, so again, you'll have one of those on there. So group numbers indicate our valence electrons. Okay. Then we got into, on your review, we're getting into what we have gone over since we came back from Thanksgiving break, which is looking at the phases and determining what is happening at each of the different points as far as phase changes go. So here it says level points 1, 2, 3, and 4 on the phase diagram. So when we look at the phase diagram, so remember, we only have 3 phases that we're going to be looking at. Okay? So your solids will be typically be in area 1. Okay. Then next to the solids is going to be your liquids, and then your gases will be here. Okay, so that has to do with the amount of, in this case, we're looking at pressure and temperature and what that's going to take to cause whatever this substance happens to be to change phases in each of these points. Okay, when they all meet together, this is what we call our triple point. You will have on your test today, or on your test, your semester exam, whenever you take it, you're going to have a graph that looks like this without my labels on there. And it's going to ask you to identify in a multiple choice setting where each of those points are. So one of the easiest ways to kind of, even if you're not sure, solid, liquid, gas, remember those are the only 3 phases that we have. But if you know whatever point that it's talking about or looking at where it's got the triple point, that might help you at least identify or eliminate some of the answers. Okay, so where they all come together is known as a triple point. But typically, we've got our solids over here. If you look here, the pressure, as the pressure increases, we've got our temperatures. In this case, this substance will stay at a solid till about 60 degrees. And that's kind of the point where it could change into either a liquid or a gas stage, depending on the amount of pressure that's applied. So we look at phase diagrams. This first section is going to be your solids. The second section over here, liquids. And then usually the bottom will be gases. The lines themselves may change and may increase or decrease in slope, just depending on the temperature and pressure that that substance reacts with. Okay, but you will have to label it. So solids are going to be over here first to your left, liquids over here to the right, upper right, and then gases will be in this bottom station where they all come together, triple point. Okay. Then the other thing that we looked at since we came back was looking at what happens when we are phase changing. So if we're adding heat and temperature. So remember, when we phase change, we're going from a solid to a liquid to a gas. So what is it going to look like as we move up a phase change diagram? So A down here for this particular one, your solid's going to be your starting point. Okay. Then as we add heat, the next long stretch will be the liquid form of that substance. And then E will end up being the gas form. So where you see those lines slope, that's indicating a new phase. Okay, so solid, liquid, gases. Okay, and we know that gases, that as you increase temperature and you add heat, that's where those gases are. Think about when you boil water. We're adding heat, that water turns into the vapor. That's why you get the condensation on the stove, or if you put your hands above it, you can actually kind of feel that the water changing from liquid into a water vapor gas. So this one here says what's happening to the heat at AC, and this one should have been E, so I apologize. Basically, the temperature is doing what? The temperature is increasing. Okay, so the heat, you're going to see here, you're adding heat, so what's happening to heat? So it's increasing. Okay, so as we move up, it's increasing. You can see where it's moving over. So added heat, moving over, increasing. What is happening to the temperature at B and D? Well, if you notice here, so the temperature is along the y-axis here. this is indicating that there's a phase change. This is where it's going through a change. So if you're going from a solid to a liquid, this is where the substance is melting. Okay. If you notice here, there's a straight line. So when we see a straight line here, and we see it again at D, the temperature is just staying the same. Okay, we're adding heat to it, but the temperature itself of that substance is staying constant as it's going through that change. So temperature stays the same. Okay, so that those pieces there. So you will have a question about this on your semester exam. And so it's going to just ask you the kinetic energy of the particles is changing in which of the segments. Okay, so again, the changes themselves, just to kind of remind you guys, okay, is occurring as these pieces are increasing here. Okay, so as it shows the increase, that's where we actually are going through the different phases. So when it says, for instance, the question, the kinetic energy of the particles is changing in which of the segments? It's starting to change here. We're starting to increase the temperature, and we're adding heat. Once you have those two elements or pieces combined, that's where we actually have the changes of state, so solid, liquid, gas form. Okay. The other things, and I did not put these on the semester exam, is we've got a couple questions about water, and then also molar mass and the percent composition. Okay. So one of the things that you will see, and I'm going to give you guys some kind of notes to as a reminder as well. It's going to ask you about, this was in the reading that we did, but over water, the dilution rate of a sugar cube. Okay. And it's going to ask you typically, like, what can you do to change the rate at which, in this case, a sugar cube would dissolve. So if you wanted to decrease the sugar cube, basically the dilution means that it's coming apart. So basically the sugar cube would be melting. If you want to decrease, you're going to decrease the temperature. Okay. If you wanted to increase the rate that a sugar cube actually dissolves, then you would increase the temperature. Okay. So whatever you want to do, whatever direction it wants you to go, depending on how the question asks, because this is a question on there and I can't remember if it's decreasing or increasing, but basically whatever you want to do to the dilution rate is you're going to have to do the same thing to the temperature. Okay, so when we talk about the dissolving, because remember, we're phase changing. As we phase change, it's adding heat or changing the temperature. Okay, so that's where that particular idea comes from. Okay, then also in terms of water. Okay, this was also part of the reading that we did. When we talk about the shape of water, that one, as long as there's no other forces acting upon it, it's going to be surface tension. Okay, so just to kind of, so your water shape, when there's no other forces, okay, so no other forces, then that's going to be determined by surface tension. Okay. Then the other pieces that we also talking about water. If we want to look at the difference in the ice and, let's say, liquid water, because there is a difference in that. It's going to ask you about which solution or what situations occur due to the fact that ice is less dense than water. Okay, so think about it. If you put ice cubes in a cup of ice, kind of the bigger shaped ice cubes, they're floating, and they are the same substance. They're just in different phases from one another. So if we're talking about ice being less dense, less dense than water, okay, then that could be where we have the icebergs that float. The fact that we have, when we're looking at frozen lakes, we can still have wildlife. Wildlife is still present, or fish are still present in there. Probably more specifically, fish are still living in there, or other organisms. I'm going to put living in the water. Okay, so these would be some situations showing where when ice is less dense than water, here's what could happen. The frozen lakes, it's that usually typically when a lake freezes, the upper level is ice, but below the ice, it actually can still be the flowing water. Okay, so ice being less dense, when things are less dense, so say I have a cup here, when things are less dense, they tend to stay at the top. So if I have ice cubes here, that's why if you put ice cubes in a drink, liquid drink specifically, or let's say you have ice water, those are typically floating. Okay. You will have to look at a graph for the temperature and solubility, which I asked you guys to do. So one of the things that I will suggest is make sure that you look at the temperature and the solubility in there and see what that relationship happens to be. And I will, on the sheet that I give you guys for your test, I'll give you some little pointers to that as well. When we look at the last two pieces, it's the things that we have been looking at over the last week with percent composition, and then finding the molar mass. And then I believe that you will also have, let's see, it'll be percent composition, finding molar mass. I think there was one more that we put on there. But I will have some helpful hints on the sheet that you're going to be able to use to help you with that. Just kind of a little bit of a reminder of how to determine those. Okay, so these are kind of the key pieces that you're going to need to know for your test. And then, like I said, you're going to have the periodic table. I don't have the numbers on the ones I gave you, so you can add those in there. Or you may have to remember those things. Actually, I'll probably write these all in on the ones. I made copies of these already, but I'll write them in. Anyway, you'll have your electron configuration chart, and then you will also have your trends. So the periodic trends pieces. So you'll have those. This will be in black and white though. So that way you can look at those to determine and to put basically your ranking in order depending on where they're at. So you'll have 1, 2, 3, 4 key pieces, because I'll do some quick notes about those other two. So take your time, read carefully. I have actually gone over a lot of the answers for your semester exam, but I know that you guys will do well. And make sure you do your best. Take your time.